Okay, we are recording. And so then let me hand things over to group 6 to present their CSD design.
Okay, so good morning, everybody. Thank you for attending our final design presentation. We are VAST, and we have designed a variable speed satellite dispenser for a CubeSat. So this is our team. We have 5 mechanical engineers working on our project, including myself. I'm a 4th year mechanical, and I'm Phoebe Delory.
My name is Dylan Balkaram. I'm a 3rd year.
I'm Joe Harmon, a 4th year.
I'm Thomas Souza, a 4th year.
And I'm Carlos Rios, a 4th year.
So as an overview of our presentation, we'll walk you through our hedgehog concept and then give you an overview of our product itself, then go through some of our specific analyses for our 6 different subsystems, as well as recap some of our unique features. And then we'll go through our cost of our prototype as well as our production models, and then wrap it up.
So when we started designing our CSD, we wanted to focus on creating economically a very cheap design, which could be obtained through the use of multiple OTS parts. Using OTS parts means that we won't have to manufacture and design these components, and just by purchasing them, we can pass these savings on to our customer. We also wanted to think outside of the box. The majority of CSDs that currently exist on the market use some kind of spring system, which means that the CubeSat will only be launched at a specific velocity. We want to create a variable, tunable solution that would allow a mission control to select what speed they wanted the CubeSat to be launched at. So we wanted to use these two and combine it with our passion for motor control. And we came up with the following solution, which uses a motor flywheel system that allows mission control to select what speed through a radio signal they want the CubeSat to be launched. And we did use OTS components to reduce the cost, and our design completely meets all the customer needs, which were specified by the Aero Team 6 CubeSat. So this is the first view you guys are going to be seeing of our final product. On our CSD uses the rail slots which were requested by the Aero Team 6 as their CubeSat design featured slots, T-slots. And our system uses a motorized, a motor flywheel launching subsystem to propel the CubeSat out of the CSD. It is mounted onto the launch vehicle using gussets, and the door is held in place with a linear actuator. So on the left side of your screen, you should see an example of our gussets. Our gussets are designed to withstand all the multiple forces, extremely large loads, which will be applied during liftoff. And on the right side of your screen, we have a zoom in of our linear actuator locked into the notch, which prevents the door from opening. When we want to launch, the linear actuator is retracted, and spring hinges will open the door. So that the CubeSat can be launched. So the launching subsystem consists of 2 motor flywheel subsystems, and as previously mentioned, the linear actuator will retract from the latch to actually open the door.
So each subsystem that we decided to go with for this concept is covered by a final design concept shown here in this table. For the mounting subsystem, we went with gussets as described earlier. The housing subsystem has a rectangular housing made of sheet metal. The launching subsystem has a flywheel motor assembly with as shown earlier. The door subsystem, it comprises of a sheet metal door with compression spring hinges. The power supply subsystem, with the aid of the Team 6 Aero team, is going to be externally powered using the launch vehicle and a power cord. And lastly, the communication subsystem uses an omnidirectional patch antenna. The first subsystem we're going to be talking about now is the mounting subsystem, which is the gussets. The customer needs and metrics are specified here, which we determined through observation would best fit the mounting gut subsystem. Customer need 1, which was to be interfaceable with 100% of launch vehicles. We decided to solve using a large amount of gussets that are set at specific distances along the bottom edge of the CSD. For customer needs 2 through 5, we decided to go with a triangular gusset design made of aluminum alloy 6061. And for customer need 11, it has to be mounted on the YZ plane of the launch vehicle mounting plane, which we also were able to do. The overall gusset design features a triangular beam support. That's the diagonal portion there with 2 wider interface plates. The diagonal portion was manufactured to minimize weight while also maintaining maximum stiffness and toughness. This beam-like portion provides additional support during loading with 2 smaller beam supports located underneath. For the gusset analysis, we determined that the part of the gusset that would experience the most deflection during the 8.5 G-force load was that diagonal beam section. So to determine whether or not this beam section would plastically deform during this load, we conducted a beam analysis on it with the diagram shown on the right. The 2 ends are fixed because they are attached to the interface plates. There are 2 pin joints which represent the support beams shown earlier, and the distributed load was converted from a lateral load that will be acting at a 45-degree angle on the diagonal beam. Naturally, the current diagram has only 1 known, which is the distributed load, and 6 unknowns, the 2 moments and the 4 reaction forces. So at the moment, it is statically indeterminate. However, in order to combat this, we created a system of equations using the sum of moment equation about each reaction point, A through D. And using this system of equations, we were able to determine the forces and moments shown on the right. Using these forces and moments, a shear force and bending moment diagram was formed. From this diagram, we discovered that the maximum shear force would be 275.439 newtons, and the maximum bending moment would be 622.668 Newton millimeters. Using this maximum bending moment, the maximum bending stress could be calculated using the sigma is equal to my over I formula, where m is the given moment, y is the distance from the neutral axis, and I is the second moment of inertia. The y variable is 2.5 according to the 5 millimeter thickness of the beam, and the second moment of inertia is 52.0083 millimeters to the 4th, because the beam has a uniform cross section. According to this, the total bending stress was 29.888 megapascals, which is well below the yield strength criteria for 6061 aluminum, which is 276 megapascals. So we were able to determine that this beam would not plastically deform during the 8.5 G loading process.
So going into our housing analysis, we wanted to meet customer need 6 by being able to use aluminum to provide natural insulation for the contents within the CSD. In addition to that, for customer need 7, we included 2 millimeter holes all around the actual housing to allow for venting. And for customer need 9, we wanted to be able to be within the 5 kilogram mass range, and we were able to achieve that with having everything, including the housing and without the CubeSat being 4.5 kilograms. Customer need 10, we were able to achieve the tolerances given to us for the CG of our housing. In addition, for customer need 13, we were able to have our housing be able to encompass the whole entire 12U CubeSat. And for customer need 17, we were able to provide a closed container, which was able to prevent 100% of the external material from being able to enter into our CSD. And we have these 2 millimeter holes there for venting to allow for venting, but it still allows materials to not be able to enter. Customer need 23, we were able to get a prototype cost for our housing and all the contents within it to be within $500. And we were able, for customer need 24, to get our costs and our budget to be just above $250,000. So with our rectangular housing, it was made out of 6061 aluminum housing, or it was made out of 6061 sheet metal. The housing has the holes and venting holes were made using a plus or minus 2,000-inch tolerance laser cutting machine. And once the box is in the process of being folded, once it's in its housing form, we would use TIG welding to be able to secure all of the panels together. So our first analysis we did was a modal analysis. We assumed that the housing would be a fixed free beam because it would be mounted to the platform using gussets, and then it would be free at the door end where the CubeSat would launch from. We performed a modal analysis to determine the natural frequency, so then we could be able to determine our shock load that would be exerted on our CSD system. And the way we did that is by using a Euler-Bernoulli beam equation for a fixed free beam to find the natural frequency. And we did this with using variables of the modulus of elasticity, the moment of inertia, and the density of aluminum. And from the first mode, we were able to find that the first mode correlated with the housing to a frequency of 101.9 hertz. And the shock response spectrum only assumes that you use a single degree of freedom system. So then we would only need to use the natural frequency for the first mode. And so after linear interpolation from the chart shown, we were able to derive a shock load of 104 Gs that is enacted on the system. So our second analysis we did was a buckling analysis, where we basically took that 104 Gs and converted it into a force. And the first thing we wanted to check was if the rectangular housing would crush. And the way we would check that is by doing a simple force over area calculation. And when we did this calculation, we were able to find that the factor of safety of the stress we found compared to the yield strength of aluminum was 21.6. However, we still want to check that the beam isn't susceptible to buckling, and that will be shown on the next slide. So for a buckling analysis, the first thing we had to do is find the radius of gyration, which was a function of inertia in the area. And then after that, we needed to determine the slenderness ratio and compare it to the critical slenderness ratio. Since the slenderness ratio that was found was much less than the critical slenderness ratio, we had to use Johnson's formula for classifying it as a short beam. And based on Johnson's formula, which is a function of the yield strength, the modulus of elasticity, the length, and the radius of gyration, we were able to find that the max load that would be needed in order for this to buckle was 165.9 kilonewtons. Comparing this to our factor of safety of what the actual max load would be applied, it would only be the factor of safety would be 6.5. And then using our stress equation, we were able to find a factor of safety compared to the yield strength of aluminum to be 4.16. So now we needed to check our structural load to make sure it was sound. We did a lateral load analysis where we basically took our 8.5 G force and we converted it into a distributed load along the side of our beam. And using a basic bending stress equation, we were able to find that the max stress that would be seen near the gusset area would be around 7.72 megapascals. And the factor of safety associated with this and the yield strength of aluminum was 35.8. And then determining the deflection, we were able to find that the deflection of this structure would be approximately 0.008 of a millimeter, around there, which is very insignificant. Lastly, we did a liquid surface tension analysis. Again, as I mentioned before, the venting holes had a diameter of 2 millimeters. The precision laser cutter we would be using has a minimum cutting radius of 30,000 inch, so this hole would be able to be made. This is a function, so what we're solving for is the amount of height of water that can be standing water that can be placed above the hole without it being able to actually go into the hole. And this is a function of the surface tension of water, gravity, the density of water, and assuming theta is equal to 0, which would mean that the direction of the water flow would be exactly parallel to the center axis of the hole. And when we solve for this, we were able to find that almost a little more than half an inch worth of water can be standing water above the hole before leakage would occur in the housing.
For our launch system, we selected 6061 aluminum rails and motors, both of which are able to withstand the full range of temperatures that can occur both in mission and during the 6-month storage period. The motors require 0 power during storage, and our system is primarily OTS parts to reduce costs, which meets almost all of customer needs. In addition, the flywheel motor, our design had a variable launch to meet customer need 19, which gives the ability to meet the full range of 1.5 meters per second and 2 meters per second. So our rail design is designed to specify is designed to meet the needs given to us by our paired aerospace team. They're manufactured using slot mills, and there are 4 rails, 1 for each corner of the CubeSat. Each rail is lubricated using PFPE, which will give us a consistent launch speed without any friction. The rails were analyzed to withstand the 8.5 Gs acting as a structural load. The 104 Gs shock load would act parallel to the rails, so it wouldn't be a direct force on them. Acting in the vertical direction, the part on the rails that would break is the section cut highlighted in red. But with the 8.5 Gs, the CubeSat would only enact about 520 newtons on each rail, with only 410 kilopascals applied over the course of the rail. That's well beneath the yield strength of aluminum 6061, gives a factor of safety well above what's necessary.
So the flywheel motor design is what really allows us to achieve this variable launch speed. Launch speed is modulated using a NEMA 11 stepper motor, which is rated for 3,000 RPM. This brushless DC motor can easily provide this launch speed that's required, and further, the fact that it's brushless also means that it is relatively reliable. The 24 millimeter diameter flywheel that's attached is made out of fluorosilicone. Fluorosilicone was chosen as this is the material which NASA frequently uses in aerospace applications due to the material's low outgassing properties. And this flywheel is going to be pressed against the T-slots on the T-slots on the CubeSat. There are 2 motors present on the design, 1 on each side of the housing, and both of them work together to launch the CubeSat out. So the first question we had to look into and perform an analysis was how quickly could this motor flywheel system launch out our CubeSat. So using the maximum rated velocity of the motor, 3,000 RPM, and taking into consideration the radius of the flywheel, which is 12 millimeters or 0.012 meters, the linear velocity that can be that is exerted using this flywheel is 3.77 meters per second. This is well above the 2 meters per second requirement that is requested from our aero group. But we can achieve whatever speed under 3.77 meters per second just by sending less power to the motor, thus using a controller. Thus, our system can easily achieve any speed between 1.5 meters per second and 2 meters per second. It's also important to make sure how much force the motor could generate. So the motor is rated for 8.5 ounce-inches, which is approximately 0.06 Newton meters. And by taking into account once again the radius of the flywheel, 12 millimeters, we can calculate that the motor can exert a force of 5 newtons onto the CubeSat. As there are 2 motors within our system, the total force generated by the launch subsystem assembly is 10 newtons. So that 10 newtons has to be compared to the force of friction. Thankfully, as this will be used in space, there won't be a large amount of static friction due to the lack of gravity. And the biggest friction we'll have is the viscous friction between the rails and the T-slots and the PFPE lubricant. PFPE was chosen as it is frequently used by NASA in aerospace applications. And at the colder temperatures we'll be encountering, approximately negative 85 degrees Celsius, it has a dynamic viscosity of 2.6 millipascals per second. When we could take into account the maximum velocity requested by our customer, 2 meters per second, the 1 millimeter or 0.001 meter distance between the slots, between our rail slots and the T slots on the CubeSat, and the maximum amount of area, contact area between the between our rail and the CubeSat's T slot of 0.0029 meters squared, we can calculate the total force of friction that will as the CubeSat is being launched out. And it was found to be only 0.008 newtons. As there are 4 railings, the maximum frictional force is 4 times that, so 0.032 newtons. However, since our motors can generate up to 10 newtons of force working together, the force of friction between the rails and the T-slots will not greatly affect the performance of our motor. Another thing we wanted to make sure is that the flywheel would not slip against the CubeSat's T-slots. So in order to prevent that, our motor and flywheel will be pressed against the T-slots with a force of approximately 2 pounds, which is well under the 5-pound radial load capacity that the selected motor has. 2 pounds is approximately 8.89 newtons. And using the coefficient of static friction between a dry silicone and greasy aluminum, which is approximately 0.8, we can calculate the force required for it to start slipping to be approximately 7.11 newtons. As the maximum force generated by the motor flywheel is only 5 newtons, we don't have to we do not foresee any slippage occurring, which would affect the performance of the CubeSat's launch.
So these are the metrics specified for our door system, along with our solutions that encompass them. These include ensuring a resistance lower than 2.5 milliohms for safety and ensuring a closed container to protect from external materials from entering and affecting the CubeSat. It was also found that it takes less than a second to open the door with no low power needed while it's in storage. And the materials are also able to weather the required ground storage time, and our design has all of the parts secured to the CSD to avoid any pieces detaching and polluting the space environment during launch. So this is our door design, and our door design subsystem consists of an aluminum sheet metal plate that acts as the main door, and it's attached to the housing with 2 spring-loaded hinges. And the door also has an attached latch via fasteners as well as TIG welding. And in the closed position, this latch interfaces with the linear actuator motor to keep it closed, with the spring hinges compressed so that when the linear actuator motor retracts, the door springs open. And we analyze the door to find the bending stress to determine if it fails under the determined shock load. And so this is made out of aluminum 6061 with an elastic modulus of 70 gigapascals and a yield stress of 276 megapascals. And so first we found the moment of inertia using the geometry of the door. And then we took that and translated it into the force that the shock load is going to exert on it using the mass and the 100G shock load. This resulted in a force of 936.8 newtons. And we decided to approximate this as a beam using the side secured by the linear actuator acting as a fixed joint with the hinge side acting as a pin joint. And we can then divide this force that we calculated by the length of the beam to figure out the distributed load that would be exerted on the door itself. And this was 3,750 newtons per meter. And so we used all this information to calculate the maximum bending moment exerted on the beam. And that would be 29.3 Newton meters, which can then be translated into a bending stress by multiplying by the distance from the neutral axis, which is half the thickness of the door, and then dividing by the moment of inertia calculated to get a bending stress of 112.7 megapascals, which is less than the yield stress. So it was determined that the door doesn't fail under the shock load.
The second analysis that we conducted on the door mainly involves the amount of time it would take for the door to open when the launch signal is given. As described earlier, the door uses a set of spring hinges with compression springs to force open the door when the linear actuator retracts from the latch. The natural position of these springs is at a 180-degree angle, so naturally straight. It is forced to a 90-degree angle to close the door, which imparts a certain amount of, which generates a certain amount of torque. This torque is about 0.03051 Newton meters, and using the mass of the spring and door, which was 0.00232 kilograms plus 0.955 kilograms, and the radius of the spring, which was attributed to the squared radius of the outer spring loop minus the squared radius of the inner spring loop, we were able to determine an angular acceleration. Using the torque is equal to inertia times angular acceleration formula, and replacing the inertia variable with a 1/2 mr squared expression, we were able to determine that the inertia is equal to approximately 6.7583 e to the -7 kilogram meter squared. And reworking the equation to solve for angular acceleration, we were able to find that it is equal to 45,144.432 radians per second squared. Now, following that, using the following two relations, which are that angular acceleration is equal to angular velocity squared times radius, and that angular acceleration is equal to angular velocity divided by time, we were able to determine an angular velocity value by square rooting the quotient of angular acceleration with radius, the outside radius in this case, which resulted in an angular velocity of 5,620.643 radians per second. And reworking the angular acceleration is equal to angular velocity divided by time formula to solve for time, we were able to get that the total amount of time in ideal conditions for the door to open would be approximately 0.1245 seconds, which is well within the 2-minute time frame given.
For our power supply, we are utilizing the 28 volts supplied by the launch vehicle through a DB9 connection port. Given the needs change halfway through the year, the act of using the power that's provided to us meets every solution, every metric, and provides us with no need for to have an onboard battery. So for the entire power, we receive the 28 volts through the DB9 connection port, which then transfers to power an Arduino Uno and multiple digital potentiometers. The digital potentiometers then distribute the power to each subsystem in accordance to the signals produced by the Arduino Uno. The Uno acts on interprets and acts on the signal received by the patch antenna, which I'll describe shortly. The entire system, I need to go back. The entire system draws a total sum of about 1.6 amps, which is well below what would be necessary to bother any of the wires, as it would require about 4.8 amps per wire, of which are 28 gauge copper wires coated into silicone to produce any thermal issues. Our communication system utilizes the EnduroSat patch antenna, which is designed to full CubeSat specifications, originally designed for it to be used on a CubeSat. It has a full temperature range that will survive in both emission and storage conditions. It acts on the X-band frequency as specified in the metrics and requires no power before use. X-band antenna is small. Even in the full shock load of 104 Gs, it only exerts about 1.7 kilopascals on the housing shell, so it won't cause any structural damage. And based on data provided by the manufacturer, it complies with standards for GEVS and ESA, which are both standards made by NASA for parts used on the exterior of satellites. It has passed space testing in both vibration and thermal fields. It'll be fully operational the entire mission.
So to recap a couple of our unique features from our design, we have rails on the inside of our housing that interface with our air group's T-slots, as well as a unique flywheel motor assembly for our launching system. And our door subsystem utilizes a linear actuator motor, as well as the rest of our subsystems utilizing an Arduino for interfacing with each other.
Now for the cost analysis, I will be going over the prototype section. Since we got it explained to us that the prototype would be purely testing the functionalities and capabilities of our design instead of the structural integrity or space fitting or any other factors like that, we were able to slim down the cost considerably by mostly 3D printing the major components while being able to keep the OTS parts that were necessary for testing. This is reflected by the $55 price for raw materials, which is for a 2,300 gram spool of PLA filament, which will be fed to the 3D printer, similar to the ones offered in Mech2 Lab. As for the OTS parts, the fasteners were not included due to pricing, and instead it will be the pieces will be connected either via a combination of interlock welds and epoxy adhesive. Since this is mostly going to be done with a 3D printer, the manufacturer labor is neglected. However, for energy, since the 3D printer does require energy to operate, the GRU City of Gainesville commercial cost per kilowatt hour was used to get a total energy consumption price of $16.25. Assembly labor was conducted using a Boothroyd and Dewhurst handling and installing time chart. And the total cost to assemble was calculated as $118.37. Manufacturer tooling and design labor were also neglected due to the fact that limited amount of tooling will be necessary to construct this prototype, and it is under the impression that the prototype will be produced by us, leading to a total price of $499.28.
For a full-scale production run of one unit, it costs about $6,500 for OTS parts and raw material. It'll be about $40,000 in tools, but that only needs to be paid once, and then that can be used for any more units produced. $1,300 in total labor, about $60 in electricity based on GRU costs. Ultimately, it comes to just over half of our $50,000 budget, and the tooling wouldn't need to be for every unit, so we have plenty of left over. So why VAST? Our solution uses primarily OTS parts, which means we are incredibly competitively priced, and we use the variable speed flywheel launch mechanism, which means that our launch speed for satellite position can be changed up until the launch signal is sent.
So we'd like to thank you for attending our final presentation and your interest in our CSD design, and let us know if you have any questions.
Okay, great. Thank you for your presentation. We did end up starting a little bit late because, like I said, I got here a little late from the Aero team. So we'll run maybe about 5 minutes over the actual planned session, which is meant to stop at 11:30. So we'll try to aim to stop at 11:35, which gives us just over 10 minutes for Q&A. So let me hand things over, or first question over to, well, any of our panelists. So Alex, you're unmuting, so you're first.
Yeah, so I just wanted to ask, so it's like I haven't been experienced with any of this project. So this is going to piggyback off of some lunar mission to get up to orbit and then get into some like low orbit around the moon or something.
Yes. In we're piggybacking off the SLS missions, the for instance, the Artemis missions,
Okay.
and that will take us all the way to the moon, at which point our CSD will be used to shoot out a CubeSat.
So then going off of that, there's a couple points where you did like a beam analysis where like I know in the gust analysis, you used gravity as like the weight of the beam to get a force. Is that just the force of gravity while it's sitting on Earth? Did you like take into account if this launches into space, you're probably getting uh 2 or 3 times the gravity on the thing? Is that accounted for
Yeah.
in how it's in the Artemis capsule?
Yeah, that's exactly where we got those values from. Was from NASA.
Okay.
They have documented the expected loads, especially most notably during liftoff. So, for instance, a structural load, the structural force that is acceleration that is felt throughout the launching process, for instance, is about 8.5 Gs.
Okay.
So 8.5 times the force of gravity, 9.81 meters per second.
And I guess no one else has another question. You had this L bracket type of design to hold it down to something. Um, why'd you decide how to design the voids in the space of the diagonal support for the L bracket? Because that's just if it is an OTS part or is it something you're going to machine?
So that is something we're gonna machine. Basically, what we're gonna do is we're gonna in our cost analysis, we have stock that we bought, and we would basically take like a bandsaw, cut them into like separate blanks and then CNC them. And basically the way we determine like the triangulated like holes within the diagonal portion of the gusset was by like doing FEM. So we would like do design iterations where we would like take the gusset and we made it like way overbuilt, and then we would put it in, and then we would do hand calcs to verify like critical locations, similar to what Carlos was showing in his analysis, because that diagonal portion had most of like the concentrated load. So that was just a hand calc to verify our FEM. And so we just did that in like a design iteration standpoint to see how much we can like shave off in our weight while still being able to withstand that load.
Okay, and then did you account for any of the price in terms of machining, like how much it's going to cost to machine out those holes in relation to how much strength you're going to gain and weight you're going to lose? Or did you
Yes.
just go purely on weight?
So weight was a big factor. We did do a cost analysis on it as well, because we did know manufacturing would have been a big deal. I think Carlos could speak on that because he did a lot of the cost analyses for like manufacturing processes.
Right. We did do a Boothroyd and Dewhurst handling and installing time for assembly. And as for manufacturing, we were considering the overall price for equipment and machining or for tooling, as well as labor. The main labor that we considered for the gussets involved just mainly the bandsaw as well as the CNC machine. Weight was the more or less the deciding factor with creating the final design for these gussets, since we noticed as the weight was able to be shaved off in considerable amounts while not really losing as like a considerable amount of strength and overall.
Okay.
I have a quick question for the gussets as well. Could we go to that slide? I think it was in the beginning. Oh, perfect. Thank you. So I had a few questions. So for that triangular part, is that manufactured separately and then attached to like the L bracket, or is this all like one block?
So that would be all just one block that's machined. It would be machined on the CNC in different operations. In the triangulated portion, we put like little fillets there because we would be able to get a small like 16th thou of a inch end mill, which could be able to go in there and get those pockets because an end mill wouldn't be able to get like very sharp corners. So we accounted for all the tooling that would be needed to make this. But yes, it would just be one giant like piece. It wouldn't be welded or anything like that.
Okay, and for these little L brackets, how are they being attached to the main body through rivets?
So we used fasteners. We used, I believe, what Carlos, do you remember what size fasteners we used?
I
I
know those M5 fasteners, and we
M5.
would Loctite them as well
Yeah.
as added security.
Oh, okay, so they're like bolts.
Yes.
Yes.
Okay, and follow up to that, was there, just like out of curiosity, like a calculation done for tear out? Because these have to be held on to like a vehicle, right? And so there's a ton of forces that are going to be applied on those M5 fasteners. Was there like a shear calculation done to take that into consideration?
We did look into it a little bit, yes. I don't have the calculations with me at the moment, but we did look into how an appropriately torqued M5 fastener, how much load it could withstand. And we found that it was able to withstand the majority of the loads, all of the loads that would be applied. And we would just be using Loctite as an added level of security for fastening it down.
Okay, and how did you guys end up choosing M5 rather than like any different size?
It was one of the smaller fasteners which would which were strong enough for this. Somewhere I also even have the grade of fastener which we were using. I don't know it off the top of my head, but we did
That's okay.
we did take that into consideration.
Okay, thank you.
Okay. Other questions? Ria, oh, there you go. Okay.
Yeah, so I think you had a part that had like a 600 factor of safety. Can you go back to that slide?
Yes, that was our rails.
Is there a
It's
reason why you're going to keep it at 600? You could save, whether it be cost or weight or whatever, because that's very overkill.
The thickness of that part is only 4 millimeters.
Oh, okay.
Additionally, we had to make it out of aluminum so that we wouldn't have negative material because that was the material that our aero group was using for their T-slots, and they requested us to use the same material or similar material to prevent any negative so that the two materials would interface. Yeah.
Yeah, they kind of locked us in with that design because of the way that they had designed their stuff. So we kind of had to work around what they had. Otherwise, we would have changed it to have a lower factor safety.
Awesome. Good job, guys.
I had another quick question regarding the flywheel motor design. Yeah, just out of curiosity, what is holding that flywheel to the motor shaft?
A set screw.
Okay.
Does this get used at all while it's in space, or is it just while it's like does
It's
the
just
motor
used
operate?
in space. The motor
Is there any
is
like vibrational like concern with the set screw with zero gravity and the set screw unscrewing itself?
that is a good question. We didn't look too deeply into that, truth be told. We don't imagine it would be an issue. For the most part, we did look into a little bit the vibrational for a lot of the other fasteners, and we didn't see any problems with it. But we didn't take into account that set screw.
Yeah, I mean,
That
I don't
was-
know very much about vibrations, but I know in space, you know, anything that spins is gonna cause some type of issue in the entire system.
That is something we'd have to look into a little
Yeah.
further. Yes.
Another quick question. Are those rails with the T slots, are those designed by you guys or is that provided?
That is designed by us. The aero group we were partnered with gave us the specifications of the T slots they were including in their CubeSat, and since we were building a product to work with their CubeSat, we had to design our own rails. So I think we mentioned it in one of the previous slides that the rails would be we would manufacture the rails in-house using slot mills to actually provide to create the T slot. And yes, if it wasn't for that, we would have selected probably something off the shelf to save manufacturing time and cost, but we didn't have a choice. We had to make something that was custom made for our group.
Okay. And for the rails, are those like inner edges are like in the picture you had before, they almost look like little sharp corners. So I was just wondering if there's like really small fillets on that to help with dispersing stress, or is it just like sharp corners?
There should be there's a really small fillet on the upper corner inside the T slot. We should actually have them. I don't think that this image shows them. It's a very small fillet too.
Okay. Yeah, I was talking about the inside portion.
Yeah, it's a very small fillet. It's one that would be manufactured with the T slot, with the slot mill. But
Okay, thank you.
Okay, so we're now really at the end of time because we got to transition to the next presentation after this one. So so we'll wrap it up there. I want to just thank you guys one last time for sharing your presentation with us this morning, and more generally for your enthusiasm and energy and creativity, and particularly your patience with me over the span of the semester. So depending on who you ask, either Mech 2 or Mech 3 is considered to be like the final boss, like the hardest class in terms of just time demand in the curriculum. John Brooks refers to Mech 2 as the final boss. So
It's Mech 2.
yeah, well, yeah, no, you got it from a former Mech 3 TA there that it's actually Mech 2. So yeah, just want to kind of congratulate you guys on getting through this final boss, and really, to be fair, it's kind of a rite of passage in our mechanical engineering curriculum. I think you guys have done a fantastic job this semester. So it really just, I appreciate your persistence and grit, and taking everything very seriously and getting to this point. It's a major accomplishment to have gotten this far, and to have done as well as you guys did. So thanks for that. I think with that, I do need to say one more thing, which is please fill out your course evaluations. Fill out your course evaluations, because there's an extra credit opportunity if we get a 95% completion rate. I think we're about 75%, so we're almost there, but there's only about 12 hours left. So remember to do that as soon as you guys sign off. So let's see. With that, let me stop recording.